Hello everyone. Welcome to the last installment of the video lectures on Bootstrap Sweep generator. In the previous lecture, we have seen how the sweep is formed, and we have also computed the voltage that it reaches with reference to the time constants, voltages, and the gated pulse, the time for which the gate is open. Now, let us try to look at the condition at which the bootstrap circuit is at the end of the sweep. So, it could be the sweep could have reached a voltage Vs which is less than Vcc, or the voltage could have reached Vcc and remained there. Whatever may be the condition of the final voltage to which the capacitor has reached, it could be Vcc or less than Vcc. Once the gate is over, the gate pulse is over, you can see here, when the gate pulse is over, the base voltage of the transistor Q1 will again become positive, and this will force the transistor Q1 to go into saturation. So whatever is the final voltage here, the capacitor must now start discharging in the opposite direction. So whatever charge is accumulated here will start discharging as soon as the gate pulse ends. That means the voltage across the capacitor at Tg has to start falling down. Okay, so this point you remember. Now, to know the rate at which it falls, we need to first look at the original condition during the sweep. So let us do a small revision. We started with the capacitor having no charge, so the voltage across the capacitor was 0. So the point, this node was at literally 0, and this capacitor C1 charged to Vcc, and this end of the capacitor held a voltage Vcc. So this was Vcc and this was 0. So literally this and this, these two nodes are same. Okay. Now the capacitor started charging towards Vcc. As soon as the capacitor voltage increases, remember Q1 is cut off, because as soon as the gate pulse is given, Q1 is cut off. When the capacitor voltage rises slightly, then please observe that the voltage here increases, it becomes slightly positive. The voltage at the output also becomes positive. Obviously this is the voltage available at the output. Now this capacitor, one end is Vcc, okay, and this end is increasing. So automatically the potential here must be increasing exactly in the way the output voltage is increasing, because this is not connected to any ground. So this both ends of the capacitor are floating in the sense, if this voltage increases, this voltage also has to increase. So initially, before the capacitor started charging at this location, at this time, the voltage here was 0, the voltage here was Vcc. Okay, the diode almost has a 0 voltage across it. It's almost reverse biased. But once the capacitor starts charging, definitely the diode will go into reverse bias. What is the meaning of that? The meaning of that is the capacitor C1 is holding a voltage Vcc, and it is having enough charge. Please remember, its value is very high. C1 is very large. So it will hold a huge charge, which it can use to supply the constant current to the resistor and ultimately to the capacitor. So from the time t equal to 0 up to time Tg, this capacitor is going to supply the current IR to the capacitor C. So the current is not coming from VCC. Please remember this point. The current is not coming from VCC. It is coming from C1. Point number 1. And as this voltage increases from 0 towards VCC, this voltage also will increase. The voltage here is VCC and it will start increasing VCC plus V0, and this is V0. With the result, the voltage across C1 will remain constant. Okay. Now when the voltage at the emitter keeps on increasing, you remember the collector is held at VCC. The collector is constant at VCC and this voltage is increasing. So ultimately it has to reach some point VCC. Then what will happen to Q2? Q2 will go into saturation. So it will no longer work like a buffer. It will no longer work like a emitter follower. So it will reach VCC and it will stop there. That is why we said it can only reach up to VCC. It cannot cross that VCC. Okay. Now that is the condition. So at the end point at Tg, the capacitor is having a voltage VCC across it and it is having some charge. Okay, and this capacitor is holding a voltage VCC here. Emitter has become VCC. No longer it is going to increase. So we are at that position. We are at that position. So what is the voltage across R? It is VCC. What is the voltage here? This is also VCC. And what is the condition of Q1? Q1 is cut off. Okay, that is the condition at Tg. Now we will remove the gate pulse, which means we will make the base go to positive. Now what will happen when we make the base go to positive? Suddenly this jump will reflect through the capacitor at the base and the transistor will be driven into saturation. So Q1 will be forced to go into saturation. So how will it go into saturation? Unless it is receiving current. So we have to understand that it has to, the current that must flow through Q1, which is IC1, must be equal to the saturation current. Now what is that saturation current? That saturation current is VCC by RB, which is the base current, multiplied by HFE. Okay, so IC1 will be equal to VCC into HFE by RB. That I have mentioned here. Please see here, HFE into VCC by RB. So you can see here, normal time the collector current is VCC by R, but just when the transistor is going into saturation, the current that has to flow through IC1 has to be equal to HFE times VCC by RB. Okay. Now who will supply this current? Where this current will come from? This current is not coming directly from VCC. You see the interesting point here. At this node, this capacitor is already charged. Okay, and it can supply the current because now this voltage is going to 0. The transistor is going into saturation. So obviously this capacitor has to supply part of the current that IC1 requires. Then this resistor, because of this capacitor C1, which is already having some charge, it can also supply the current to IC1. And IB2 is approximately equal to 0. So IB2 does not matter. So we will have a relationship that IA plus IR has to be equal to IC1 according to Kirchhoff's current law at this node, ignoring IB2. So we will write it down. So IA plus IR is equal to IC1. So what is IC1? IC1 is VCC by RB into HFE. That is this value, VCC into HFE by RB. And what is IR? IR will always be equal to VCC by R, because this capacitor C1 will always be having VCC. So this is VCC by R. Now what is IA? What is the current that is flowing out of this? So this current has to be following the Kirchhoff's current law. Okay, ignoring IB2, IA must be equal to IC1 minus IR, because IR is also supplying a part of it. IA will supply some part of it, IR will supply some part of it. We already know IC1. IC1 is equal to VCC by RB into HFE. So we can calculate what is the current IA. Very important. So can we write the equation now? IA is equal to IC1 minus IR, and IC1 is equal to HFE into VCC by RB, and IR is equal to VCC by R. So IA is equal to IC1 minus IR. We will write that equation here. You see this line. This line will be clear for you. IA is equal to IC1 minus IR plus IB2. IB2 is negligible. Okay. Now what is IC1? HFE into VCC by RB. Please remember this. And IR is equal to VCC by R. So now we know what is the current that the capacitor must supply so that this transistor Q1 remains in saturation. Okay. The trick here is C cannot supply whatever current it wants to. It will supply only that current which is a balance, is remaining. Whatever IR is sending, remaining part IA will be sending. So IA is equal to HFE into VCC by RB minus VCC by R. A very important equation. Okay. Now this equation is giving me the current, that is the current that is flowing out of C and emptying the charge which is there in the capacitor C. Now what is our objective now? Our objective now is to find out how much the rate of fall is happening such that the current in the capacitor becomes 0. That means the retrace. What is retrace? During the trace it reached a voltage Vs, and during the retrace, because the capacitor is now connected to Q1 here, this capacitor is connected to Q1, so the current, the charge will start reducing. So naturally the voltage will start reducing, and this will reduce to 0. We want to find out when it will reduce to 0. So what is this T? What is this time? So we have given our requirement here, that what is this time T. Okay, that means the retrace time I want to find out. That means from here to here, from this time to this time, what is this TR I want to find out. Now this T is from 0 to this time. Okay, and from here to here, T minus TG, that is called as the retrace. T minus TG is the retrace. Now how do we find the retrace? Again we apply the basic principle. So what is the basic principle here? Now the voltage Vs that is already there must become 0. So we can simply substitute here the current flowing through the capacitor during discharge is equal to IA. Okay. Now how much time it is taking to discharge? We are assuming it is equal to TR, retrace time. And what is the capacitance value? It is equal to C. And what is the voltage? Voltage is equal to Vs. So is this the correct equation? The current divided by charge multiplied by time will give me the voltage Vs, because what is current? Current is voltage by resistance, is it not? So current is voltage by resistance. So V by R. So V by R, TR by C. So V by RC into TR. So you see here V by RC into TR. Just a small understanding of this equation applied here will give us during the retrace the retrace current multiplied by the retrace time divided by the capacitor will be equal to the initial voltage Vs. Okay, so remember this equation for retrace. So now we know the equation for finding the retrace time. That means what is the time taken for the voltage to become 0? That means the time taken for the retrace. So simply this equation can be rewritten because we already know what is Ia. We will substitute here. So reorganizing the equation, TR is equal to C multiplied by Vs. Okay. Now this VCC is common in both the denominator expressions because IC1 minus IR is HFE into VCC by RB minus VCC by R. So VCC is common, that we are bringing to the numerator. So TR is equal to C into Vs by VCC divided by HFE by RB minus 1 by R. So this is how, using the parameters, we can find out the time taken for the trace to come back to 0. That means retrace time. So we found out what is the trace time, then we found out what is the retrace time. So both of them we have found out. Now that is the last stage. Okay. Now what we have to do here is understand one more very important point, that is you can see here this capacitor C1 is the main source of charge for the resistor here for supplying the constant current. Now what is this capacitor doing? This capacitor is quickly charging using this VCC and VEE to store the charge so that it will be able to supply the charge right from the time the trace is starting here and then trace is ending. Okay, remember this point. The capacitor C1 will supply the charge from 0 to T for both for charging and for retracing, discharging. Charging and discharging, it is providing the charge. Of course, for discharging it will not provide. So it is just providing for the charging, but whatever it is, the total charge is coming from C1. Now obviously what happens is this trace and retrace has to continue. It is not a single cycle. So the trace must be there, then retrace, then trace, then retrace, trace, retrace. It should go on continuously for a very long time. Okay. Now this capacitor is storing the charge for one cycle, and in the process it will lose some charge. That means the voltage across the capacitor C1 will not be VCC because it is giving the charge to C, no? So a little bit of it will be lost. Okay. Now what it should do before the next cycle starts? Before the next cycle starts, it must recover from that loss. Okay, it must recover from that loss, very important. Otherwise, at the beginning of the next sweep, the capacitor will not have VCC. So the sweep slope will be affected because of that. Okay, the total the sweep itself will be wrong. So the last important point that we have to understand about the bootstrap sweep circuit is the capacitor is enabling a linear sweep, linear retrace. Now we have to understand how this capacitor will quickly make up for the lost charge. Okay, it supplied some charge during this time t, and now it must quickly recover whatever charge is lost in the least possible time. Maybe sometimes during this time itself it will be doing it. Now this can be calculated, the time taken to replenish the lost charge during the trace retrace time can be calculated by equating two things. One is the charge lost during this time t is equal to the charge gained during the remaining time. What is the shortest time that is possible? That equation I have given here. Okay, it's a very simple equation. What is the minimum time, minimum recovery time required for the capacitor C1, that we have to calculate. Okay, what is the minimum recovery time T1 for the capacitor C1 to recover the lost charge? Now we are using the equation charge lost is equal to charge gained. Now what is the charge lost? Charge is lost during this time t. What was the current flowing? The current flowing was VCC by R. So VCC by R is current multiplied by time will give me charge. So VCC by R into T is the charge lost. We know VCC, we know T, we know R. All these terms are known. Now we will equate this to the charge gained by the capacitor C1. Now what is the time taken to gain? The time we don't know. We want it to be minimum and we are calling it as T1. Now how is the capacitor gaining the charge? Where from it is getting the charge? That is where this voltage will play the role. The hero of the, I won't call it as hero, but it is the last voltage, important analysis that we do in the, till now VE was keeping quiet with the RE. So what will happen is, just when the capacitor is about to start the next cycle, you see here this path, this is negative, RE is there, this point, it will quickly charge this capacitor C1 through this VEE. That means VEE divided by RE will be the current, because this is shorted, no, this transistor is in saturation, so this voltage is 0. So quickly this VEE by RE current, the current will flow through C1 in this direction. So obviously this point will be again going back to VCC. So we are equating VCC T by R to VEE by RE. This is the current which will help in recharging the capacitor C1. Time is T1. So VEE by RE into T1 has to be equal to VCC T by R. Okay, when we equate these two, what do we get for T1? So T1 will be equal to VCC into RE divided by VEE R multiplied by T. So all these parameters are known to us. All these parameters are known. So there is a very clear way in which we can obtain the value of T1. Okay, so please remember these points. And here in this particular case, this portion is blank because we cut it and used it at the beginning. Do you remember what we put here? We put here, whenever this sweep does not reach VCC, the value here will be what do you call VCC by RC multiplied by this point will be TG. So that is what we have put there. Okay, so if you want, you can remember that thing. So VS is equal to VCC into TG. Okay, so divided by, I'll put divided by RC. Okay, and only thing is here we have to put one line. We will put a line and end the lecture for today. Okay, so just to make it complete so that you don't wonder what we kept here. So VCC by RC into TG whenever Vs is less than Vc. Okay. Now let us quickly recap what are all the things that we tried to understand here. First of all, we analyzed the bootstrap sweep circuit, how it is formed, why it is formed like that. Then stage 2, we have analyzed the circuit just before the transistor Q1 is cut off. Okay, all the conditions we have understood. Then we have analyzed how the sweep starts, and after the sweep is reaching TG, we have seen how the gate will be closed, and then we have analyzed how the retrace will start. So when the retrace reaches the end, we are expecting the next cycle to start, but before the next cycle starts, we have seen how this VE by RE will replenish the lost charge in C1 during the trace and retrace cycle T, and that we got the equation here. So please remember, we can get the sweep time from this equation. Okay, sweep time can be obtained from this equation, and we can get the retrace time from this equation. This is the equation for retrace, this is the equation for trace, and this is the equation for finding out how much time it will take for the capacitor C1 before it is ready for the next sweep. So obviously it has to be very short time. Okay, so that is how you have to understand. Now this completes the analysis of bootstrap sweep generator. So kindly go through all the videos. I made them for classroom understanding. Take notes and let me know your doubts, and we will try to clarify them and move forward. So thank you everyone.